at a couple of important differences and similarities. A mirror. Light doesn't get through the mirror. It's getting reflected back. So for a mirror like that, this kind of mirror can form a real image as well as the virtual one. Well, it depends on the distance from the object to the mirror. A mirror like that can't form any real image. It forms only a virtual image. And for the lens, the difference is that light now actually getting through. So a lens could form a real image, but it's now going to be on the other side of a lens. Also, it would form a virtual image depending on the situation. And we know that we can calculate the focal distance of any lens if we know the index of refraction of the material the lens is made of and index of refraction of the material around it. And similarly to several important rays we can use to trace rays. In mirrors, we can use only a couple of important rays when we deal with lenses. For a conversion lens, well, this ray number 1 and this ray number 3 usually are two of the most convenient ones. When a ray is traveling parallel to the principal axis, it bends closer to the principal axis and it travels through the focal point always. And when a ray travels through the center of a lens, doesn't matter what kind of lens it is, nothing is happening to the ray. It doesn't bend. For a divergent lens, we need to use an extension. So we know, we call it a divergent lens because it diverges light. So for a lens like that, a ray should bend away from the principal axis. To figure out the exact angle, we have to use this extension. The extension now has to go through the focal point, not the ray itself, because if you would trace a ray like that, that would mean you actually using a convergent lens. So for divergent lens, ray diverge, and we have to use extension. And again, we need only two rays. Any two will work, but these two or these two are the most convenient ones. And of course, we can relate the object distance, the focal distance, and the image distance. The equation looks exactly like the equation for a mirror. We also can introduce the magnification. Again, exactly the same definition. You just have to calculate the ratio of the image size over the object size. But we have to await some agreements on distances and sizes. since we can form a virtual image or a real image. Image could be upright or inverted. We have to use this convention. So when the image is upright, the height of the image, its size, is positive. When the image is inverted, the height, the size of the image is negative. This is exactly the same agreement we used to use for mirrors. When the image is real, it is formed by actual rays. In that case, the image distance is positive, and again, it's exactly the same agreement. The difference between a mirror and a lens only is that a real image formed by a lens is formed on the other side of a lens. The real image, which is formed by a mirror, is formed on the same side of a mirror where the object is. That's it. However, in all cases, an image distance is positive if the image is real. And of course, the image distance is negative if the image is virtual, which means it is not formed by actual light rays, it is formed by extensions, like in this situation. Well, and now we're just going to answer several questions. This is one of the questions. What do you think about this lens? These are all the numbers. The first surface has a radius of 1 meter. Second is a less curve. The radius is 1.5. The index of refraction of this material is 1.5, some kind of a glass. However, it's immersed into some kind of a liquid with a higher index of refraction. Of course, with all the numbers, we actually can calculate the focal distance, but my question is, just tell me, is it a convergent lens or divergent lens? And just to remind you, when the focal distance is positive, it's supposed to be a convergent lens. When the focal distance is negative, that means the lens is divergent. Convergent, positive focal distance, divergent, negative focal distance. So to answer this question, we just need to figure out if the focal distance is positive or negative. We don't need to know the actual value. Well, close to 50-50. Let's see. This is the first surface. When the first surface is concave, what does it tell us about the radius? What is a rule? Anyone? Yes. Well, the rule is not about larger or smaller. The rule is about positive and negative. These numbers could be positive or negative. When light encounters a convex surface, the radius is what? Positive or negative? You need to just remember that. It's not an equation to you, just in case we need to know the rule, this particular rule. What does it say? Anyone? Positive. It's related just to the shape of this surface. It's not related to anything else. When light encounters a convex surface, the radius is negative. So this light encounters first concave surface, so R1 is negative, and then another one, so R2 is negative as well. So what we have is 1 over some negative number, negative 1 minus 1 over negative 1.5. So this combination, is it a positive number or a negative number? Should I always ask Paris question? Tell me. If you think it's a positive number, raise your hand, please. If you think it's a negative number, please raise your hand. Well, it's negative 1 plus something smaller than 1. So it is a negative number. So that's a negative number. And we are multiplying by another number. The first combination of variables also is negative or positive. So that's a negative number. This length is 1.5, medium is 1.8, minus 1. It is a negative number again. So we have to multiply two negatives. The result is what? Positive. When the result is positive, that's supposed to be a conversion length. That's how we think it through. Well, a similar question. Now we don't have any numbers. So if you read the problem, it says this lens, which looks kind of like that, is thicker at the ends than in the middle. All lenses either thicker on the ends or thinner on the ends. That's it. There are only two options. If the lens looks like this, it's not a lens. To be a lens, it should have different thickness. And if it has different thickness, we have only this option or that option. That's it. So this question is about this option. The lens is thicker here, thinner there. And we also place it into a medium with index of refraction which is lower. So n medium is less than n lens. The two conditions. Well, first of all, I want to ask you a question. What do you think about that red dye? Red dye. This is what I want to ask you first. if you look at this shape, you should state specifically the relationship between the radii. If you think the first radius is greater than the second, press 1. If you think the first radius is smaller than the second one, press 2. Now I want to erase this, and I want to switch to my system, and I want to start it, and go. Now I forgot. So what was my first choice? R1 is greater than R2. R1 is greater than R2. And the second choice, R1 is less, smaller than R2. Right. Numbers do not change anymore. Well, again, remember, if you're flattening the surface, that means you're making the radius larger and larger. So R1 in this situation is smaller than R2. This surface is less curved, more flat. So R1 is less than R2. Well, in magnitude, of course. Now, if you want to make an estimation for this thing, we need to use actual values for each radius, which means it might be a positive number or it might be a negative number. For a concave surface, the radius is what? Negative. So it's minus this, minus this. This is just a repetition of the previous situation. So what we have here, again, is some negative number. However, what can we say now about this combination? Which index is lower? Lower. Medium has a lower index. Medium has a lower index. So this ratio, again, is it greater than 1 or less than 1? Greater. This ratio is greater than 1. This difference is greater than 0. So now you multiply the positive number and a negative number. The result is what? Negative. If the result is negative, this length is what? Divergent. Any questions? Okay, let's move on to ray tracing. Please take a sheet like that, or just use your note and notepad and draw a ray diagram for two additional situations. This picture shows you a case when the object is placed between two important points, a focal point and a double focal point. Remember, a mirror has two important points, a focal point and a center of a mirror, which quite away from the mirror as a focal point. So, similar, 2 points are important for a lens. And this picture shows you how the image is formed when the object is placed between the focal point and the double focal point. So we need only 2 rays, 1, 2, the image. Well, first of all, you look at the picture and you can say something about the image, it's what? Real. It's larger. And the object is, and it's inverted. So, can you tell me, right now, for this situation, the magnification, M, is it greater than 1 or is it less than 1? Again, if you think the actual value of the magnification is greater than 1, you can press 1. And if you think it's less than 1, you can press 2. Well, 75% failed. I'm not happy about that. I'm just stating the facts. The magnification, by definition, is this ratio. And we know that the rule says when the image is inverted, the size of the image is supposed to be negative. So that's how we can write it mathematically. Which means the magnification is a negative number. Any negative number, especially a large negative number like -5, is less than 1. So the actual value of magnification is one thing. The magnitude of magnification is another thing. If I ask you a question about the magnitude, you will be correct. Because of course, the magnitude of the magnification, the magnitude, the actual value, is greater than 1. Because the image is larger. However, the actual value is negative. So don't forget about this. Now, please move your object behind the double focal point and retrace the rays. Basically what you're doing, you're moving the object away from the lens. And I want to ask you a question, what is happening to the image? In particular, is it getting larger or smaller? To figure out the answer, you're supposed to draw this ray diagram and look at the image, the new image. So, you're moving away the object. The size of the object, of course, doesn't change when you move it. You do not invert it, you keep the same orientation. So what's going to be happening to the image? Of course, first of all, it changes its location, but in addition, it changes its size. So, and when we talk about change in the size, we talk about the magnitude of its height. Yeah. So what is happening to the magnitude of its height? Is it getting larger or smaller? So if you think it's getting larger, you can press 1. If you think it's getting smaller, you can press 2. Again, divided volts. Well, first of all, again, remember that all this mathematics works only for rays which are very close to the principal axis and for the thin length. But since the length is very thin, its thickness doesn't matter. And usually, when we draw a ray diagram, we even don't show the shape of the length. We just draw a straight line like this. Not really straight. Like this. You can ask, what kind of lens is it? So to show what kind of a lens is it, we just use the symbols like that. For a conversion lens, you can imagine that it means the lens is shaped like this. For a divergent lens, we will draw a straight line and we will mark it like that. And that actually makes your diagrams more accurate because you don't have to consider aberration. So let's say 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. The focal distance is 6 blocks. So the double focal distance is 1, 2, 3, 4, 5, 6 more. 12 blocks from the lens. You want to place the object behind this point, so somewhere here. The object is 3 blocks tall. So 3 blocks tall, like that. That's it. Now, 1, 2, 3, like this. Now, the first ray, which is parallel to the principal axis, is supposed to go through the focal point. It would be nice having a ruler, but that's the first ray. And the second ray always is the easiest one because it doesn't bend. You draw it directly through the center of the lens. When rays cross, that gives you the location of the image. And if you draw it very accurately, you actually can, without any calculation, you can say the new size of the image is supposed to be 2 blocks. Well, 2 is less than 3, so the image shrinks. Plus, what is happening to its location? Well, the original image was 1, 2, 3, 4, 5, 6, 12, 13, 14, 15, I think 18 blocks away from the lens. The new image is just 6, 7, 8 blocks away. So when we were moving this object away from the lens, the image was moving closer, getting smaller and closer to the lens. Well, where do you think is going to be the image formed when the object is infinitely far away? When the object is infinitely far away, there is no angle anymore between the rays traveling from the object. All rays are parallel, and parallel ray travels through the focal point. So the image is going to be at the focal point, and it's going to be very, very small. Now, let's tell me that the same lens, 1, 2, 3, 4, 5, 6, the same focal distance. And now we want to place an object here. Between the lens and the focal point. Please draw the picture. Look at the image and tell me, in this situation, is it going to be larger or smaller than the object. Again, when we talk about magnification, it could be tricky because magnification could be negative. When we talk about size, we always think of positive numbers. We just compare magnitude of the height. So the height of the object is 3 lux. We know from experience the image could be larger or smaller than the object is. So in this situation, for this case, 1 for image being smaller and 2 for image being larger than the object is. Okay. Lens 1, 2, 3, 4, 5, 6. Focal point. The object. Well, what do we know? This ray. Well, how does it travel? Is it going to go closer to the principal axis or away from the principal axis? What do you think? Towards? Does it bend towards the principal axis or away? Well, it's a convergent lens, of course. So the location of the object doesn't matter. The ray which is parallel to the principal axis goes from the focal point. That's it. The ray which is traveling through the center of the lens doesn't bend at all. If you look at this picture, do these rays converge? No, they diverge. So they cannot form a real image. That's the first fact. When rays converge, what do? We draw extensions. These extensions show the location of the size of a virtual image. That image is virtual, it's not real. If you place a screen here, you can look at the screen and you will see the image. If you place a screen here, you will not see anything, just nothing here. Because there is no actual light over there. You could see a virtual image, but you would have to use an additional optical device, your eye, for example, if you were looking like that. In that case, your eye, because it's a lens, would converge divergent rays on the retina, and you could see something. Well, but the question was about the size of this image. Well, again, it's virtual. It's upright, so the magnification is going to be greater than 1 in actual value, and it's larger than the object is. And of course, you can ask different questions. For example, if you want to form an image which is larger than the object, Can you use a conversion lens? Yes, you can. There are actually two options. One option is like this. Second option is like that. So a conversion lens can provide a larger image, either real and inverted or virtual and upright. In the lab, you have seen or you will see a device like that. This is a light source, a lens, and the screen. If you look at the screen, you don't really see anything. But of course, by manipulating with a source or lens or a screen, you can actually achieve, well, again, I missed it. But at some point, you can actually achieve a clear image of the object. The object is a filament of this bulb. So, when does it happen? It happens when the object distance, the image distance, and the focal distance of this lens related by the lens equation. How does the lens equation look like? Again, very similar to the mirror equation. You just have to write this equation, and if you know any two variables, you can calculate the third one. If you know, for example, you have a ruler and you can measure the object distance and you can measure the image distance, you can calculate the focal distance. Or if you know the focal distance, you can calculate, and you know the image distance. Yes, I haven't been moving this screen, so the image distance was fixed. You can calculate the object distance, the location of this object, so it would give you a clear image. Well, and well, in the lab, you will be answering the questions like, what's going to happen if you cover a half of a lens? Or what's going to happen if you cover a half of a filament? I'm covering the top half of the filament. What is happening to the image? The bottom part of the image disappears. Why? Because the image is inverted. Well, you also might figure out a way to make the image as large as possible or as small as possible. We saw that by moving the object, we could change the size of the image. Well, if your lab setup gives you a certain length, you can use only this length. So, to achieve the largest image possible or the smallest image possible, what do? You need to make the object and the screen as far apart as possible. And then if you move the lens in between, at some point the image reaches its maximum possible value, at some point it reaches the smallest possible value. Well, of course, we don't need to talk about a divergent lens. Divergent lens is much simpler because for a divergent lens, if you move the object, what is happening? Nothing much. This ray always tends away from the principal axis, so its extension travels through the focal point. This ray, or this ray, or this ray, always is straight, doesn't bend. So the image is formed here, when the extension crosses the central ray. And we can see in this situation the image is upright and it's virtual, yeah? Because we have to use an extension of a ray. And even if we place an object here, still what's going to happen? This ray doesn't change. The ray travels through the center of the lens, doesn't bend. So that's going to be the image. Image is again in the same region between the mirror and the focal point. And again, it's upright, and again, it's smaller than the other face. So this is the only situation for a divergent lens. It cannot form an image larger than the other. Another situation. Now you don't see a lens. Well, still, you know the rule about rays. You know that this ray, number 3, should connect the top of the object and the top of the inverted image. So if you draw a straight line like that, this point should give you the location of the lens. So the lens is supposed to be here. Now, what kind of lens is it? It's a real image, so it has to be a convergent lens. What do we know about other rays? Well, if the ray is parallel, it's supposed to travel to the focal point. So first of all, it should end at the same point where the first ray ends, but also it should cross the focal point. So this point is supposed to be the focal point of this lens. And we now know some numbers. So what do we know? We know that the object distance plus image distance is supposed to be 3 meters. And we know that the image is a half of the object. What does it tell us about magnification? Well, we don't have many choices. It could be 1/2, it could be -1/2, 2, or -2. So what do you think the magnification is equal to the actual value of the magnification? The image is smaller and inverted. Smaller means, I'm not asking that question, but smaller means the magnitude is supposed to be less than 1. Inverted means the actual value is negative. Okay? So what does it give us for magnification? Magnitude is smaller than 1 and negative. -1/2, exactly. So this is the magnification. And if you want to write all the equations, well, first of all, object distance is always positive, but for a real image, image distance is also positive, so that's 3. Now, magnification -1/2 is supposed to be equal to negative image distance over other distance, and this expression involves actual values. So if you had a virtual image, the image distance, this number di would have to be negative. Plus, we can write another equation for focal point. And that answers all possible questions. We can calculate the object distance, image distance, magnification, focal distance, everything. Good exercise to do at home. Well, a straightforward problem. We don't have to solve it, but let's just draw a picture. Focal length is 30 centimeters. Last 30, a divergent length. That's the focal distance. The figure is placed at 75 centimeters away. 75 is twice, even more, yeah, than 60. So 30, 60, 75. Here. Now we can say what's going to happen to the image. The image is supposed to be inverted and it's supposed to be smaller. And if we apply the thin length equation, we can calculate everything. And one more minute, which conversion length. Here, divergent length. Negative 30 centimeters. Divergent length. So we start from a length. That's the focal point. Another one. And the figure is placed at 60. So 60 is 30 times 2. So the figure is placed at double focal point. But we know it doesn't really matter for a divergent length. One ray travels like that. Second travels like this. That's the image. Virtual, upright, smaller. I would think all these topics which are related to the last test are trickier than topics we've learned already, because there are more kind of not very straightforward questions. One of these questions might sound like, this, when you need to figure out what kind of optical device you could use to form a specific image, larger, smaller, upright, downright, or in combination. My general advice always just take a minute and draw all possible ray diagrams you can. It literally takes a minute. So if you have a conversion length, 1, 2, 3, 3 important locations, focal distance, double focal distance. This ray is the same for all objects, no matter where the location is, and it goes through the focal point. And now it's blue. Yeah. Okay. However, so this ray travels through the focal point. However, the ray which travels through the center of a lens gives you every time a new location of the object. Here, the object is larger, upright, virtual, and let's say here the object is real, downright, smaller. And another quick diagram is for a divergent lens, and for this lens, it basically doesn't really matter where we place an object, the image is always smaller, upright, virtual. And now, if you have a question, what lens should you use to form a virtual image? You should say what? Any. They both could form a virtual image. If you have a question, what lens should you use to form a virtual image which is larger than the object is? In that case, doesn't work. Only this lens might give you a virtual image larger than the object is. Well, now we need to take a look at practical applications of this theory. For example, the photo camera. What's happening? Well, here, instead of using a knife, which converges light on the retina, we just use a screen. But of course, we can use a screen only when the image is real. So it might be one lens only involved or several lenses, doesn't matter. The image has to be real. So in that case, we could use a photofilm or a special LCD sensitive screen in a digital camera. And the real image, well, either results in some chemical reaction if you use a photofilm, or some electrical signals if you use digital camera. And our eye is an additional optical device we use. Of course, it's kind of a very complicated device. It's amazing how nature could make it good for us. The lens is only one part of this optical device, but the lens actually focuses the light on the retina. And a healthy eye, or average person, of course, it's all true for average person. Different people might have different features a little bit. So for a healthy eye, the closest when the eye actually can focus the image on the retina is about 25 centimeters for a healthy eye. And the largest distance possible, basically infinity. When the object is infinitely far away, all light rays are parallel, and the relaxed lens focuses the light on the retina easily. That's how a healthy eye works. So, for people like me, the problem is that the lens cannot focus light on the retina for objects placed farther than a specific point. For all objects, well, between 25 centimeters and some specific point, which we call far point, lens can actually provide the image on the retina. However, if we place an object farther than this point, in that case, that's what's happening. So what do? Well, the idea is simple. We want to diverge these rays a little bit more, so they would focus on the retina. So we have to use a divergent lens. Mathematically, what would we do? Well, we always say that when a system has many lenses, in this situation it has two lenses. First lens forms an image, and then second lens uses that image as an object. So here, when we place a divergent lens, what do? We want to form an image of this distance object at the far point of that person. Or different person might have different far point depending on this distance. Some person might use very strong, some not so very strong lens. So what we want to have that distant object which is at infinity, and we want to form its image at this point. Well, of course, this has to be a virtual image because it is a divergent lens. And we can write an equation for this particular lens, a lens equation. 1 divided by the focal distance is supposed to be equal to 1 divided by the object distance plus 1 divided by the image distance. If the object is very, very far away at infinity, so this fraction, 1 divided by infinity, is just equal to 0. And that means this image distance, which equals far point of the eye, supposed to be equal to the focal distance of this lens. So basically, well, there are many different ways to find out what kind of lens should we use. One of these ways is to make a person look at an object, make it farther and farther away, and eventually, when the person cannot see it clearly, that's the far point distance is reached. You measure the distance, that's supposed to be the focal distance of this lens. Well, nearsightedness or myopia, some of you might know better even than me how it works. Maybe medical students, especially. Now, farsightedness. That's a different kind of problem. Now, again, a regular person can clearly see an object up to 25 centimeters to the eye. And farsightedness means a person cannot see objects clearly starting from some larger distance. And that's what we call near point and of an eye. It happens because now the lens is not so flexible anymore as in a healthy eye. So for close objects, the image is actually behind the retina. So now we want to converge the rays a little bit more. So now we have to use a convergent lens. And again, we can apply the same kind of reasoning. If you have an object placed somewhere here, like you want to read the paper, so what do? You want to make an image of this object at the near point of this eye. Again, to measure this near point, what you can do, you can look at something and move it away from you, and when you're, when you can see finally clearly this object, that's your near point. And now, that's going to be the object distance, that's going to be the image distance. So you can write again the lens equation. And this image now becomes being an object for this lens, an eye. Well, and if you wear glasses, you know that nobody tells you the focal distance. They tell you this. They tell you the power in dioptries. By definition, this is just inverse focal distance. High power lens, what does it mean? So if this value is large, that means this value should be small. Because the numerator should be smaller and smaller, make the fraction larger and larger. The focal distance is small, that means light, when it's getting through the lens, bends strongly. That's what it means. High power lens. Yeah. Low power lens, that means radius, and the focal distance is large, so light doesn't bend so strongly. lens, you always can apply the thin lens equation as many times as many lenses you have. In this example, there's one lens, it forms an image. So you can write the equation for this lens. Then this image becomes an object for the next lens. And you can write the thin lens equation for that lens. And, well, for two lenses, these are all possible equations you can write. First lens, second lens, the magnification for the first lens, the magnification for the second lens, the total magnification, and the ratio of the final size divided by the initial size. And, well, if you have an optical device like that, try to look inside spyglass after. So, when you move eyepiece relative to the object, that's what you do. You change the distance between the focal points of those lenses. And we always can add one more additional condition just from geometry of the situation. This solves all possible problems. One specific case. What if we place two lenses together? And of course today I didn't take any lenses. Well, and I broke the microphone. If you place them together, that means the image distance of the first lens and the object distance of the second lens together add to 0. There is no now space between the lenses. It looks like that. So pure mathematics, just nice exercise, gives you this, a very simple result. So the effective power is just equal to the sum of individual powers of the lens. So if you put them together, the power of the total system equals power number 1 plus power number 2, maybe number 3, maybe number 4. In particular, let's say you have two lenses with the same focal distance. However, one lens is divergent, another lens is convergent. Like this. This is a convergent lens, and this is a divergent lens. One has a positive power, another has a negative power of the same magnitude, and when you place them together, what happens? It's not a lens anymore, it's just a brick. So D1 plus D2 in this particular special case equals 0. Well, or you can form, well, you can place many other lenses together like this. In that case, your total power will be larger than individual power of each lens you're adding up positive values. Well, another special case, a telescope or a spyglass. Again, we have to say, in addition to all the equations we've already written, we have to say that the object is very, very far away at infinity. We just move it away. Plus, to relax an eye, we want to be rays getting out of the eyepiece parallel to the principal axis. Because when these rays are parallel, remember there's an eye here. When these rays are parallel, that's the easiest situation for the eye. It easily converges light from the retina. To make these rays parallel, we have to place this object, which is image generated by this lens, at the focal point of this lens. So to achieve that, we just make this distance equals to 0. So two conditions. First condition, this isn't infinitely far away, and second, these two focal points coincide. And in that situation, again, pure mathematics. Well, first of all, these arrays also become parallel to each other. That means this image distance also is very far away. And in this ratio, what we have is two very large numbers divided by each other. So it gives just 1. And in these equations, when object distance infinitely large, we just cross it, turn out, and this focal distance equals this image distance. In this equation, this term is 0. So now this focal distance equals this. So we use these expressions, and that gives us the magnification of a telescope. It just equals the ratio of the focal distance of the objective over the focal distance of the eyepiece. The first telescope had been developed, created, invented by whom? Very famous person, you know that person. Not personally, it's been many, many years ago. But you've heard his name many, many times. Anyone? Galileo. He used the telescope and he found that actually even the sun has some spots. That costed him a lot. So, he actually used divergent lens for the eyepiece. Doesn't really matter. All equations say it's just the focal distance for the eyepiece is negative.